Good morning, everybody. Thank you for joining us for today's webinar, Analyzing Piston Ring Failures. I am Amanda Harmoning, and I will be moderating today's event. I'm an admin assistant here at AERA, and joining me today from AERA is Rob Monroe.
Good morning, everyone. Yeah, Rob Monroe here. I look after membership and technical development with AERA. And today, Amanda and I will both be in the background. We're going to be looking at any questions that you have for the webinar, and we'll get those over to Bill at the end of the presentation. And Amanda's going to show you how to use that questions box. And in the next few slides, I'll show you how to do that. So I'll go back to Amanda here for just half a sec.
All right. First off, there are a couple different ways to listen into today's webinar. You guys can call in via phone and just make sure you enter your access code and audio pin so your line stays muted during the presentation. The other way to listen in is just via your computer's mic and speakers. And again, just make sure you select that radial option so that you have the correct settings and can hear everything. Plus, then we're able to make sure that everyone's lines are muted so there's no background noise. A couple other things to know, there is a grab tab. That's the little orangish red box with the arrow in it. This allows you to collapse and expand your control panel during the presentation, so it's out of your way while you're viewing Bill's presentation here in a bit. And then the last item is the questions box, and you'll find that at the bottom. And if at any time you have questions, comments, anything, go ahead and type those in there. And as Rob mentioned, we'll be in the background reading those. And we'll do a Q&A at the end with Bill to get those questions answered. So at this time, I'll switch things back over to Rob and we'll get rolling here.
All right, thanks, Amanda. Just a few housekeeping slides here before we get started. I did notice that there were a few people that have not been on our webinars before. So for those of you who do not know who AERA is, we are a nonprofit association that are made up of engine professionals that include builders and rebuilders. We've got installers as well as some distributors and manufacturers reps as members. We have school members, we have government members, and we're over 2,000 members worldwide. Now AERA for 2019 is celebrating its 97th year this year. So we've been helping engine builders with technical specifications and information since 1922. So we've been around a very long time helping you with your information and specifications for all your engine needs. For those of you that are not members of AERA, well, you need to be. I mean, this is really an inexpensive program. You're probably better off on the shop floor making money, do what you do best. Allow us to get all that engine information over to you, do all that research and everything for you. It'll just save you lots of time, which in turn will save you money. It is only $324 for the year when you include your $75 contingency connection coupon, and that's for a typical active US member shop. So it works out to only $27 a month to be a member. So any questions on that, we can also help answer those throughout the presentation, but we would encourage you to be a member of AERA. It is a great program. Looking at what we got going on for 2019 for regional conferences, busy year. We've got 6 on the go for this year, with the first one out in Michigan on March 30th, which is Motor State Distributing. You'll notice in your control panel, there is a little thing there, the little tab that says handouts. If you click that, Amanda has uploaded a PDF file of the brochure of Motor State Distributing. So in that brochure, it does list who the presenters are. There's 7 presenters for that presentation in Motor State. So that regional is going to be very popular. This regional is also going to have no cost involved. So we would encourage you to get registered and get your name so you can get a seat in there. It's going to be a great regional. Looking forward to that one. Sun and Products on May 3rd is out in Missouri. We've got Bakersfield College May 18th in California. TriStar Engines August 9th out in Wisconsin. Then we've got Liberty Engine Parts September 14th, which will be in Pennsylvania. And our last one for 2019 is going to be out in Rottler Manufacturing in Washington. It's in October. We just haven't got a date nailed down for that one, but looking forward to that one. So 6 busy, really busy regionals coming up for 2019. And again, you want to try and get out there and get to see one of those. All right, so for today's presentation, we'll get started. A lot of you know Bill, and a lot of you probably have been in his presentations before. Bill is one of our technical pioneers of our industry, and a lot of them, like I say, you probably know him and have had the opportunity to learn from him. So without further ado, I'll get started with today. And good morning, Bill. How's it going this morning?
Hey, everything is good, Rob. All the ice melted off the trees yesterday, and now it's just crunchy on the ground when you go out. So things are looking good here in Northwest Ohio. How about you? Everything good?
Yeah, everything's good. No, that's good. We're for those of you that are on the webinar, obviously you can tell we're not all in an office. We're Amanda's out in sort of in the Chicagoland area, and Bill is out in Ohio, and I'm up here in British Columbia. So this is the nice thing about technology. We can put on a presentation like this for everybody.
Outstanding. So I'll get going. We'll talk later when we get done and answer questions. So let me get going. Many of you know I worked for MAHLE for 37 years. Matter of fact, I retired from full-time employment there in May of 2018. And it was kind of the best of both worlds. I could sit home on days like yesterday when we had ice and not worry about driving 85 miles to work. And at the same time, they've given me the ability to do some part-time work here and there. And one of the things I get to do is webinars and presentations. And today's is on piston rings. So what we're going to cover today, just so you know, we're going to talk a little bit about who is MAHLE, a look at modern piston ring materials, piston ring face coatings and processes, failure analysis, and diagnosis of problems. So that's our topics for today. Who is MAHLE? Well, without reading all this corporate stuff at the top, I can tell you it's a big German foundation in the auto parts industry with about 76,000 employees, about $12 billion euro dollars in sales, with 170 manufacturing plants. Now, since we're talking rings, I wanted to talk specifically about rings in the Americas. St. John's, Michigan, just north of Lansing, about 30 miles, we make roughly 8 million compression rings a month. In Aguas Calientes, Mexico, we make lower run, smaller production oil ring numbers for the U.S. and all sorts of rings for the Mexican and Central America market. And then down in Itajubá, Brazil, we have MAHLE Metallive. And MAHLE specializes Metallive for our markets with high volume oil rings and some stainless steel compression rings. And if you're wondering about the MAHLE Metallive story here, the deal was that Ernst Mahle, right after World War II, when things were decimated in Germany, he took a piston line to Brazil and started manufacturing pistons in Brazil. And he called that company Metallive. Well, as things came back in the 50s in Germany and production was good and things were rebuilt, he didn't see any reason to keep that company. So in the late 1950s, he sold Metallive. And then in 1997, the MAHLE Corporation, of course, by then Ernst is long retired, MAHLE bought that Metallive operation back from Cofab. So if you're confused about Metallive and Cofab and MAHLE, that's the short story on what actually happened there. Oops, sorry here. There we go. So what's going on at the OE level? Downsized engines in most every platform. You're familiar, of course, with the EcoBoost, the GM high feature V6, the FCA 2.4 liter Tiger Shark, and the 3.6 Penstar. You know, all of these are downsized packages, but we look at them as basically lots of performance, high performance in small packages. And then we have the true performance engine market out there. And we've had several that you're familiar with, the 3.5 high output EcoBoost for the Raptor, the Hellcat 707 and the Demon 840 horsepower engines, Chevy's R06 Corvette engine with 650 horsepower, the 455 horsepower Camaro. And I need to put another bullet in here because Ford's just announced a new high horsepower Mustang engine as well. The 476 horsepower Lexus V8. Lots of engines with huge amounts of power are out there at the OE level. So what's going on is as those engines increase in power and output, we've seen the piston ring market change substantially. In the old days, it was cast iron and ductile cast iron. Now, for the most part, it's steel. In MAHLE original make steel, I mentioned those 8 million rings we make a month there in St. John's, Michigan. Right now, about Oh, 75, 80% of that production is steel. We still have some cast iron and some ductile in there, but man, it's going and falling by the wayside, more and more steel. Why is steel such a big deal? Well, first of all, the hardness is better. So we increase the material hardness. That improves the ring wear, and especially when we go into these small cross-section, face-section rings, we want rings that are going to wear real well. High tensile strength. That allows for a smaller and lighter ring cross-section while still maintaining structural strength. High yield strength. This is a big one, especially what we are concerned with in our business is what we call hot strength, and that is how the ring holds its strength and maintains tension in the high heat environment of an engine. It's one thing to be strong at room temperature, it's another to be strong when the engine's running at full out power. And finally, increased fatigue resistance. The life cycles on the engines are longer and longer and longer, and so we need rings that are going to work for, 150, 200,000 miles without fatiguing and failing. Now, if you're more of a graph type person, this is a little easier than the last page full of statistics. This is an easy way to look at it. What we got here on the left bar is gray cast iron. Then the next bar, the darker gray color, is ductile iron. That's PC 479 at MAHLE. If you're a Federal MAHLE customer, you might recognize this as their trade name for it is the Hellfire ring, but it's a hardened ductile iron ring. Then the next bar, that one there that's kind of an orangish color, that's GNS, gas nitrided steel. And then the final bar there is the SAE 9254 that MAHLE uses in so many applications, both OE and aftermarket. Now, most all the rings we deal with today have face coating. Certainly the top rings do. Even some of the second ones do. But if we go down chronologically, we started right during World War II with chrome plating. And it was good in the day. And it still was used up until recently in a lot of heavy-duty engines. But chrome plating's really kind of fallen by the wayside today. Not much chrome plating going on. Then we got into MAHLE, molybdenum for a proper name. And it was wire sprayed MAHLE back in the day. Excuse me. And it was good at heat resistance. It was very good with oil retention, but it was fragile and it was easy. If you detonated the engine at all, you'd knock the MAHLE right off the top of the ring. So that wire sprayed MAHLE was good in the day, but not a very good material today. So we moved back in the day from MAHLE wire sprayed to plasma MAHLE. That's a plasma arc welding process, spraying a powder, and a powder that can be blended for bond strength and wear resistance and some increase in heat resistance. So most of the world is still at this plasma MAHLE generation 1, I like to call it today. Well, MAHLE, the company, our company, we've moved, probably 6, 7, 8 years ago, we moved to a better plasma MAHLE, I call it Gen 2, and improved bond strength and better wear resistance. And we started to introduce ceramics into that powdered material. So if you're getting a MAHLE-faced ring from us today, most cases it's going to be a Gen 2 plasma MAHLE ring. Now at the OE level, we may have one or two in the aftermarket, but at the OE level, we also have a third MAHLE high-density plasma that we use at the OE level. It's better than Gen 2, not as good as HVOF, but it meets a price point for OEs who have specific needs, yet, are conscious about what it costs to make a ring. The next thing there, let me get a drink here quick, is HVOF, high velocity oxygen fuel process. Our trade name at MAHLE is HV385, and it is a ceramic material. The tooling and machinery to do this process is expensive. It's shot out of a gun at supersonic speeds inside of a controlled chamber. It actually hits the ring face with such impact that the material embeds into the face of the ring. So its hardness and its wear resistance is really good. Matter of fact, we developed, our first customer for this was Ford with the EcoBoost. And it was the only ring that would hold up in those engines for the EcoBoost. And as far as I know, we're still making all the EcoBoost rings for Ford. Next down that list is GNS, gas nitrided steel. And typically, in most all cases, that's going to be a stainless steel base. And they use a environmental chamber, and they use a process where they introduce a gas in there and actually harden the surface of the ring. So GNS, gas nitrided rings, are really hard, which is good and bad. It's good because they wear real well. It's bad because they're hard and the face is really smooth. They're not very well lubricated rings. So there are some issues with GNS top rings and getting those things not to scuff in the engine. But they serve a purpose out there. There are lots of them used out there. And so we have some GNS stainless steel rings in our product line. Probably more prevalent, both at the OE and now filtering into the aftermarket, is PVD rings. It can be stainless, or in our case, SAE 9254. But PVD stands for physical vapor deposition. And it's a very hard but better scuff resistance material than GNS. So PVD rings, whether they be chromium nitride or titanium nitride or whatever, are a really good, really tough, really hard wearing ring. Real quick, here's the plasma face coating of the old, this is what we call our premium material. And you can see in the cutaway above that plasma is sprayed into a groove on the ring face. And the material of the ring, the parent material, actually protects that MAHLE on either side. And that's because the MAHLE has a tendency, especially as it scuffs up and down in that cylinder with crosshatch, to want to break and peel out of there. So laying it into a groove and protecting it makes it last much better. So we typically do that on MAHLE faced rings. The second picture is a 500x magnification of the face itself. The little black dots you see in the picture are porosity. Okay. And the porosity is good because it gives the oil somewhere to lay and cling to. So MAHLE faced rings tend to be well lubricated rings. Hardness about 450 Vickers. Now we go to HVOF. That's that one we spray out of the gun at supersonic speeds. And you see again the process for application and for prepping the ring is the same. We cut a groove in the ring. The difference with the HVOF, look at the hardness difference. We go from 450 to close to 1200. Okay, so it's a hard material, hard ceramic particles in a soft metal matrix. So the hard ceramic gives you the wear, the soft metal matrix helps the ring seat, and you still see there's a decent, not as much, but a decent amount of porosity there to give the oil something to cling to. Now we get to the PVD ring, and I was confused at first, so I'll point this out to you so you don't get confused like me. The PVD layer with the red arrow, that is the outer edge of the ring face. The black up above it is just the black plastic reflection of the material. You know, they mount these in holders and cut them in order to do the magnification. So that's just the material that's holding the ring. So what we're looking at there at the PVD area, that is the actual outer face of the ring. And you can see, in our case, it's chromium nitride. That's what we use for our PDV rings. And you can see, again, hard, 12 to 1600 on the Vickers scale. So a hard, long-wearing material. So enough about rings and production and ring materials. Let's talk now about component issues. And really, in our business, it doesn't make any difference if I was talking about rings, bearings, pistons, valve trains, gaskets, whatever. You know, if we're dealing with component issues and we're trying to minimize failures and we're trying to handle those things, it all starts with something called process control. And frankly, folks, it makes no difference whether your shop is one person or whether your shop is hundreds. It really doesn't make any difference with process control. And the next step to point out is all employees have to be on board. Now, if it's just you, that makes it pretty easy because you either sign up and you're on board or you're not. But you know, when you've got a shop operation with 20 or 30 or 500 people or more, and you got one person or two that aren't on board, you got issues, or at least potential issues. So with process control, it's really important that we have everybody in the operation on board saying, yep, I believe we're doing the right thing. So how does process control work, in case you're not familiar with it? It's simple. And again, it's simple whether it is you doing it for your own one-person operation or whether you're doing it for a big operation. And the first step is we got to identify everything that can cause us a problem. Now, we're talking rings today, so we're talking about identifying everything that be an issue with rings. And then once we identify, we got to document what are the variables, what can go wrong, you know, what do I need to have control of to make this work. So then once we've identified and documented the variables, then we start working on a plan to make sure the variables are checked as we start the process of rebuilding or remanufacturing. Now, I could hear some of you, if you didn't have your sound turned off, I could hear you right now saying, that's too much work for me. And somebody else says, oh, that costs way too much. You know, all that time I spend there, I could be honing engines and sending stuff out the door. And then somebody else says, oh, I don't worry about it. My ring and piston supplier, they take care of all the application specs. I don't need to worry. And then somebody else says, my employees are the best. They never make mistakes. You know, they've been here for years. Okay? So my response to all of you is, can you afford an engine failure related to a piston, ring, cylinder issue? Can you afford one? How about two? You know, how about three or four? Well, my point is, I don't think you can. You know, just the cost of actually the physical cost of doing them over, it's high. And then you got to deal with the cost of your reputation. So I don't think you can afford a failure. So even though this is a pain in the neck to some of you when you talk about this and look at it, I think it's important. And if we do a good job on the front end, what we're talking about right here, we should see very few issues downstream from this original cylinder refinishing operation. You shouldn't be calling AERA's check line with questions about, you know, this, that, why isn't this working, etc. So the key really is to do a good job up front. So here are the key processes, at least some of them that I outlined when I sat down and did this. And again, you're going to say, oh, well, that's simple. Do we have the correct ring for the application? Well, folks, it's not so simple today. The year, the make, the model, the VIN, the application, the fuel, what state it's sold in. You know, there is a bunch of stuff that affects the application of the ring for that particular engine. And if you don't have all that under control, you're just shooting in the dark, you know, saying, well, it fits, must be okay. Well, maybe it isn't. So the next thing is, let's assume we nail that first one down. We've got good support. We've got good people. You know, we've got good suppliers that are helping us with this data. The next thing is, are we turning out cylinders that are round, straight, and the correct size? Think about that. Three simple things that we have been preaching in our industry for years and years and years. But how do we know? Are our cylinders round? Are they straight? And are they at the correct size? Okay. Well, obviously, how we know is gauging equipment. So that gets into a whole new story. We could take a segue here for about 20 minutes and talk about gauging, gauge calibration, etc. But what you need to be thinking about is, do I know for certain in my operation that our cylinders are round, they're straight, and they're the right size? Okay. The next one. How do we identify the correct cylinder finish? Wow, this is the big one. Matter of fact, this comes up about every time we do a webinar, every time we do a presentation. Okay. It is important. Usually what happens in our industry, it gets pushed back and forth from one part supplier to another, to an equipment supplier, etc. It really is important that you nail down this surface finish information. And then even more importantly is, can we create that finish in our shop with our tools and our operators? Okay. So if you don't feel real confident about this, you know, when you're taking this, and you know, Amanda and the ARA is going to supply you this presentation, so you can take this and make notes on it when we're done. Is if you don't feel real good about this, make a note here and say, hey, I need to start digging into this more. Are we getting this thing nailed right? Okay. Then the next thing, often easier again said than done, are we sure that the rings, we got the right ring? We know that from the first step up there, but are we sure that we got the right piston? You know, the ring lineup, the piston groove, the backspace, etc., it changes frequently in modern engines. So we're not only dealing with rings here, we're dealing with a piston that the ring has to go on. So we got to make sure that we got the right rings and that we got the right pistons. And then finally, do we know for sure which is the top ring, which is the second? And we're assuming you're going to know what the oil ring is, but are we also certain that we have each of those rings on the piston facing in the right direction? Okay. Now I put a warning there because, again, this is not as easy as it once was. Many rings are torsional twist. Many of them have a bevel on the inside edge. It's a dead giveaway. It's a torsional twist. However, if they have a Napier groove on the outer edge, that creates torsional twist in the ring. However, you can have rings that appear to be rectangular and have torsional twist to them. They look square on all four corners. That ring looks identical from one side to the other, but it's got torsional twist. They would be steel rings. We make them at MAHLE. That's how I know they're out there. We make them at MAHLE. And what we actually do, the rings are real thin. You know, we're talking now a millimeter, 8/10, 9/10 of a millimeter face width, really skinny rings. And what we actually do is we coin those rings. We use them in a die, and a die has a convex shape to it. And when we push that rectangular ring, that little steel ring, into that die, it actually coins it, and it causes some torsional twist into that ring. Excuse me. So we can get that without even knowing it. So you've got to be very diligent about your rings and identifying them. And then not only do you need to be diligent, but whoever's building your engines and assembling them. Because it's so easy to get one of these rings on upside down. We have major issues. Okay. Next one. Can we get the rings on without damaging them? Easier said than done. So I'm not going to get into this because we'll be here for longer than I'm supposed to spend, but you need to make sure you got a process to get the rings on the piston without screwing them up. Okay. Are we sure our cylinders are absolutely clean just prior to engine assembly? Matter of fact, I was in a shop one day. I won't, well, I'll tell you, it was in Texas. That won't narrow it down too much, but big shop, and they washed all their blocks in a big jet spray machine after all the machine work was done. They were bragging to me how clean everything was. Well, then they took all the blocks, and they had a little corral on the floor. They had like 30 blocks there, all sitting on end in a little corral, all clean. And they sat there until the assemblers came and got them. Now, sometimes they sat there for a day and a half. Hot in Texas, no air conditioning, the doors are open, the forklifts driving back and forth. How clean do those blocks do you suppose they were when they went to the assembly department? Just giving you something to think about. Finally, do we do a final check just before lubing the rings and sliding the piston ring in the cylinder? All the rings should float back and forth in the ring grooves. You should be able to take your fingers and gently move them side to side, and they should slide back and forth. If they don't, it's time to figure things out. We got a problem. So here's the problems we see. Okay, we see assembly issues. Okay, before assembly and during assembly. So assembly issues, could be all those stuff we just talked about there. So I'm not going to go back and beat on those again. The next one I haven't talked much about, and that is abrasion damage. That's where the ring has seen an abrasive environment and it's worn the face of the ring down. What could cause abrasion? Oh, wrong surface finish. Those blocks that sat out there on the shop for 2 days after they were cleaned and got dirt and dust in them. Okay? There are a number of things, but these are the things that we see. If you were to say to us at MAHLE, what are the biggest 2 issues you have with rings? Probably number 1 is assembly, getting them in the engine. And number 2 is eliminating abrasives that cause so much damage. Now, the results we see, we have issues and we have results, I guess, or problems. Excessive oil consumption, excuse me, poor engine performance, and blow-by. So, how do you start the diagnosis process? Well, my thinking is we want to do everything possible in diagnosis while the engine is still together and running. Once it's all in pieces and laying back in your shop, it's much more difficult to figure out what was going on here. Man, I don't understand it. This thing looks pretty good, but we want to do all we can while the engine's still running. Okay? So here's some thoughts again for you. Oil consumption is kind of a nebulous issue. And so I would say first, have we documented with our customer the oil consumption? How much oil was consumed over X amount of time? Have we done the very simple documentation? Have we got the right filter? Have we got the right oil? And believe it or not, have we got the crankcase capacity nailed down? It's easy or relatively easy to have an engine over full of oil. Dipsticks get swapped around, issues happen, so on and so forth. If we get too much oil in the engine, we're going to have windage, we're going to have lots of oil on the cylinder walls, and good potential for oil consumption. So again, these are simple things, but you always want to start and nail down all the simple things first before you start digging deeper and deeper and deeper. Next thing is, have we checked for external leaks? I walk up to the vehicle and I see the whole bumper in the back of the vehicle is covered in dots of oil. Well, that would tell me we got an external leak going on here somewhere, okay? So that would be the next step. Have we checked for external leaks? Then have we looked for internal leaks? Internal means the oil isn't getting to the outside, but it's getting into the engine and being consumed through some sort of internal problem. I just ran into this about a week ago. A friend and customer called me and they were just having fits with this engine, trying to get it to run right. And they had done everything. They had all kinds of tests and stuff. And you know what it turned out being? The intake manifold had not been tightened down by the installer who brought the engine in. And so it was sucking oil, sucking air, running lean, So it can be as simple as an intake manifold fit or tighten. Valve guides, valve stem, seal issues, etc. All these things we want to look at before we start ripping things apart and tearing it down. Are we getting oil from the top of the engine back down to the crankcase? Is everything working on drain back? Next, have we done a compression test? Have we done a static leak down test? I know this is really old fashioned, but I'm an old guy, so I still like a static leak down test, pressurizing the cylinders. I told these guys when we were talking about this manifold problem, before we'd figured it out, I said check first with the piston top dead center, both valves closed, and then check again, bottom dead center, both valves closed. But sometimes you'll find out that we got an issue, and you can tell it from a static leak down test. It's a valve, it's bad, or you've got air coming out the crankcase. But it's a relatively inexpensive, easy to do test. Blow-by. This is what we refer to technically, and again, this is not due to you all, but we're talking about compression or combustion gases getting into the crankcase of the engine, okay? They call it blow-by because theoretically it's blowing right past the piston rings and down into that crankcase, okay? So what could cause blow-by? Well, the ring's not sealing well to the cylinder. Could be an issue. Maybe they're scuffed. And we got another slide on scuffing, so I won't say any more here. Okay. Rings are worn out. Now you say, well, we just put them in there. This thing's only got 1,000 miles on it. Well, maybe it was overfueled. Maybe we washed the cylinders down. Maybe we wore the rings out. You know, there are issues here, but that could cause blow-by. A broken or damaged ring, or lands underneath that ring, or piston material failure. You know, these could all be blow-by issues. How do rings seat in the cylinder or seal into the cylinder? Well, it's pretty simple. The top ring is loaded with compression gas. It comes down past the top of the piston. It gets in behind the ring and forces that ring out against the cylinder wall. Okay? And it's that compression gas loading the ring that causes it to seal. The ring tension, all that does is give you some tension to create enough compression to get the engine started. Once it's started, then combustion gas is going to seal the ring. In addition to all the stuff up above, we could also have issues if we didn't have enough side clearance on the ring. Probably not an issue for a production shop using, you know, factory replacement style pistons and rings, but when you get into performance, this can become an issue. So we want to make sure we got enough side clearance on the ring. Ring installed upside down. We talked about rings being directional, but they can be installed and have been installed upside down, and that can cause an issue. Okay. Ring gaps aligned. That can be a cross angle issue, or ring gaps too big, or ring gaps too small. Okay, so you can see here there's a lot of stuff that could enter into this. Scuffing. I told you how to slide on scuffing, and it is a big deal today. And technically, what is scuffing? Well, it's when the ring welds itself to the cylinder wall. Okay. Now, of course, the piston's going up and down, the engine's moving, so when it welds, it's a momentary weld, and then it immediately breaks away. Well, when it breaks away, that welded spot is rough. And there's material from one to the other, moved from one to the other. And I will guarantee you, it's not self-healing. It's not the kind of deal that, oh, if we just run this for another couple hours, it'll cure itself. When scuffing occurs, it's permanent. So scuffing is a bad deal. Now, it's hard to scuff a ring. I want you to know that to start with. The old traditional MAHLE faced rings, whether they be HVOF or our Gen 2 or whatever, they don't scuff. That molybdenum doesn't weld itself to the cylinder wall unless it reaches 4,200 degrees Fahrenheit. So, you know, it takes a lot of heat for a ring to scuff. What's the biggest issue we have? Is probably lack of lubrication. That's down in one of those bullet points, but that is a big issue today. What else enters into it? We got engines that we talked about in an early slide with lots of performance, high levels of performance. Those high levels mean more heat. More heat means less or more opportunity to scuff. We can run less oil on the ring pack than ever before. We don't want oiling issues. You know, we have to meet government EPA standards. We can't be consuming oil in the engine and meet those standards. So we don't have a lot of oil on the ring pack. Okay. Our OE customers, they run relatively lean fuel mixtures. Again, we're trying to reach economy standards. We don't want a lot of hydrocarbons. So mixtures are lean. Lean mixtures tend to be hot. Okay. And then finally, high cylinder pressure. These high output engines with compression ratios higher than they used to be, they create high cylinder pressures. Okay. So all those things kind of work together to create more scuffing issues than we had probably 10, 15, 20 years ago. So what do we do to reduce scuffing? At the OE level, we look at rings that can carry some oil and have some materials that resist scuffing, okay? And that would be the MAHLE rings that we talked about. And then in our book, PVD rings more so than GNS rings. So PVD does a better job resisting scuffing than the GNS material. Matter of fact, coating strength versus scuff resistance. This is an interesting little chart. On the far left is the basic plasma MAHLE. PF251 is our name for it, but basic plasma. And you can see in the scuff resistance, that bar is pretty high. And I mentioned that MAHLE is really porous, so it holds a good bit of oil, and it will stand 4,200 degrees Fahrenheit of heat. So it's a good material scuff resistance wise. The problem we had with that early MAHLE is the bond strength isn't so great. Okay. Next we went to the premium MAHLE, that Gen 2 stuff that I mentioned to you, and you can see we got pretty good improvement in bond strength, and we've given up nothing in scuffing resistance. So it was a good move for us. PVD, superior, really good bond strength, and pretty darn good scuff resistance. So as I mentioned, it's a pretty good ring. That Firepower 479, aka Federal Mogul Hellfire ring, really good bond strength, because really all it is hardened ductile iron, so there is no bond to anything. So it's superior, but it's not particularly good on scuff resistance. Gas nitride steel, same thing. There is no bond there, so it's up at the top of the chart. The HV385, that's our supersonic process for applying MAHLE to rings. You can see it's really good. Good bond strength and really good scuff resistance. That's why it works so well for Ford on the EcoBoost. That's why we offer it in a lot of OE and aftermarket replacement premium applications. It's a really good material, real premium material. So this is the chart. End gap. I think that was on another chart back there. We talked about too little or too much. And what we want is we just want a little more than the ends buttoned together at operating temperature. Easy for me to say sitting here in Ohio, but that's what we want. Now the old rule of thumb, and it's not a bad place to start for minimum, was 4 thousandths end gap per inch of bore. So 4-inch bore Ford, 4 times 4, 16 thousandths minimum end gap. Now for stock replacement sets, we usually allow more than the minimum spec. So I don't want you all to go home from this webinar today and start calling your ring supplier saying, hey, your ring's got too much gap. So we usually allow more than that minimum. Now, if you go down to the final bullet points, you'll see why. Every thousandth the bore changes end gap by pi, 3 thousandths and some change. So if we were to give you a ring at 16 thousandths, the bare minimum for a 4-inch bore, and you at some reason you were at 3-inch 998, 2 under that, what is your end gap? Well, it's no longer 16, it's 16 minus 6 and some change, so 10 thousandths. And you could have issues. So we don't know, as ring suppliers, I'm not just speaking of MAHLE, but all of us in this business, we don't know for sure just where you're going to end up. So we like to leave a little more end gap, minimum end gap, than the bare minimum, just so there's some leeway. And frankly, on stock engines, it isn't a big deal. If we got a couple thousandths more end gap, not a big deal. Now the second ring gap, let me get a drink. Rule of thumb, not a bad one. Now, when we say rule of thumbs, what that means is we'd be a lot happier if you went to the OE and said, this is the ring spec for a 2011 3.5 liter EcoBoost, whatever. We would really like that. But if you can't do that and you can't find that, then a rule of thumb is not a bad place to go. So rule of thumb for top, we just gave you. Rule of thumb for the second is 1.25 times the top. Okay? So for instance, let's say we got 20 thousandths on a top ring. So 20 thousandths times 1.25 is, I think that's 24 thousandths, right? Okay. So we would like that second ring gap to be right around 24 thousandths, 1.25 times the top. Actually, my math's not too good. I think that's 25 thousandths. So anyhow, why the bigger gap? Well, it goes back to a slide here several slides ago when we talked about what causes the ring to seal in the cylinder. Remember, we talked about compression gas coming down, working its way past the top of the ring, and then getting behind the ring and forcing it out into the cylinder to make it seal. Well, what happens is after that cylinder fires, we always have some excess gas that gets down there, and that gas can get between the top ring and second ring. And if it gets trapped there, the next time the cylinder fires, it's very difficult to get more gas behind the top ring to load it again because we got a block there. We got gas trapped between the two rings. So the OEs figured out here a decade or so ago that it would be advantageous to open up our second ring and allow that trapped gas to get out, get past the second ring and down so that we don't have these issues. So it's pretty standard today in naturally aspirated engines to run a second gap about 1.25 bigger than the top. Okay. You also see a lot of you, if you're doing engines today, you see a lot of scraper second rings, Napier second rings, if you will. They got a relieved edge, outer edge on the bottom side when they're in the engine. And believe it or not, that little bit of relief there provides gas relief, helps the gas get past that second ring and relieve the pressure, and again, allow the second ring to load again the next time the engine fires. So, good rule of thumb. So let's talk about poor engine performance. Man, I better crank it up here too. I think I'm about done, but we'll talk about it. So, look at the things beyond our area of influence. It's so often we get the blame. Well, I ran fine and then I had it rebuilt. Now it doesn't run, so it must be your fault. Well, not necessarily. So what are we looking for on the diagnosis? Well, we're looking for codes. Has the engine set any codes? Remember, the engine needs, nowadays, a good hot spark. Not just a good spark or a spark, but a good hot spark. It needs fuel at the proper time, and air and compression in order to run. And remember, what do we really have control of? Compression. All the rest of that, that's beyond our sphere of influence. Okay, well, I did figure it out about right here. I forgot that. I took a couple slides out yesterday so we'd have more time for questions. So at this stage, I guess it's question time.
Super. Thanks, Bill. Yeah, we appreciate your presentation. Lots of information there. You did mention, and we do get a lot of component failure questions on the tech line. So, that oil consumption and ring failure, it's sometimes easy to point our finger in the wrong direction. So, got that whole list that you had there of all the different things to check was well noted. So, very good presentation. Yeah, I think Amanda was going to start. I think she's got some questions there for you.
Maybe she froze. It's too cold in Chicago.
First question that came in, was, is there a preferred way to clean the cylinder when assembling the engine?
Yeah, now I'm really going to give my age away here, but hot soapy water and a bristle brush has never been beaten for cleaning cylinders before you build the engine. I don't care what high-tech machine you've got or anything. Hot soapy water and a bristle brush is the preferred method of cleaning. I used to buy my brushes from Goodson. I probably can't mention that on air, but I used to get my brushes from Goodson, and we would have a bucket and hot water, and man, we would scrub and scrub and scrub. And then once you've rinsed, really the key is, and you could do this in your shop. I've showed lots of people this over the years. If you want to be sure it's clean, have your guys who are doing that work every day, have them get one ready. And then just before they get ready to assemble there, it's all clean, everybody signed off on it, you come up with some clean engine oil and a lint-free piece of cloth. You can buy, occasionally get shop rags that are lint-free. What I used to use, it wasn't too high-tech, but it worked pretty good, is I would get about 10 inches or 12 inches of toilet paper and roll it up and squirt it with oil. And then I would take that little white toilet paper and I would rub it up and down on the cylinder wall in an area, maybe 2 inches or so. And if that paper comes out oily, but otherwise clean, you're good to go. If there's some black on that paper after you rubbed it, guess what? That thing isn't clean. And it needs to go right back into that cleaning process a second time. So I can't tell you how important that is to get the abrasive out of the engine. And we as engine builders, we're the culprits in putting most of them in there. So we really got to work hard to get them out. Any more, Rob?
Yeah, you betcha. Another one's come in here. Let's have a look. How does the situation change with heavily turbocharged or power, different scenarios with ring gap using, pier rings and heat transfer and that sort of thing?
Well, of course, the more heat you have in the top of the engine and on those rings, the more end gap you need. And I'm going to waffle around this and make whoever sent this in probably mad because it won't be the answer they want. But what I sold rings in the drag racing market for years, Top Fuel and Funny Car, nitro motors, alcohol motors, all that stuff. And we talked it, and they had the advantage, of course, on a good weekend, they're going to tear the motor down 8 times. So we had the advantage of getting pretty quick gratification. And it was simple. What I would tell them is the same thing I just told you. Minimum end gap should be just shy of the rings touching. So we would pick a number, maybe whatever they were using, we would look at it after we had the engine apart. And if we didn't see any signs, any shiny areas on the butt ends of the rings, and this is top ring predominantly, but if we didn't see any areas that were shiny, we knew that the rings weren't expanding and butting at the end gap. Okay? So what I would say then is if it was, let's say they had 35 thousandths, I would say, all right, build another motor. Next time you build the motor and gap the rings, and save the rings for me to see the next time I came and looked at them. But you look at them yourself, and you take a little pocket magnifier and you're looking for any shiny area on the butt ends of the rings. And if you see that shiny area, your ring gap is too tight. You don't have enough gap, so you need to open it up. If you don't see any shiny area and you have the ability to narrow the gap up and try another, next build, ideally you'd like to narrow it up a little bit. So it's a touch and go operation, but the tighter the gap, shy of butting, the more you keep the cylinder pressure up in the cylinder and the less you have escaping past the ring pack. When you're making power, it doesn't do any good to have compression gases down in the crankcase. You want to keep them up above. So hopefully I answered that, Rob.
Okay. Here's a good one, and I know this one is sort of something that we get in the shop all the time. Will the rings line up during the operation of the engine? So the gaps in the rings?
Not if there is proper crosshatch. And in the old days, and I can whip this rule of thumb out again, but I really don't trust my rules of thumb if you can find info. In the old days, this was a standard like 4-inch bore engine. We would want between 22 and 32 degrees of crosshatch. That was off of horizontal, upwards. And if you've got that kind of crosshatch somewhere in that 30 degree, it can be 35. It varies more and more today than it ever did back in the day. But if you've got that proper crosshatch, your rings aren't going to line up. If you don't have a proper crosshatch, your rings could line up and could be lined up when you take the engine apart.
All right.
I think that
Here's
was
one more for you.
Okay.
Yeah, one more. Here's another one for you. Does the break-in procedure vary between the various MAHLE ring facings, or MAHLE ring facings? It's in MAHLE, your company.
Okay. I'll think for a minute. No. Matter of fact, the break-in procedure doesn't vary a bit, nor does, frankly, the cylinder surface finish requirements. They are what they are. And frankly, we're not the folks at MAHLE or my good friends on the other side of the state there in Michigan at Hastings. We're not the people who give you the cylinder finish specs. We don't invent them. They come from the OE, and the OE has a specification for that surface finish. Our rings will run on that OE specification perfectly, okay? And you don't need to do anything different in your shop, whether you're running a PVD top ring, or whether you're running an HV 385, or whether you're running the Gen 2 MAHLE. You don't have to change anything you do for our surfaces on the rings. But again, don't be looking at us ring suppliers wanting us to give you all the specifications, because we're not the folks that create those. They're coming from the OE.
Okay, so a couple of questions, Bill, have come in about oil consumption. And I think probably some of this might be just more of an opinion, because I don't know if there's some serious documentation on it. But the question goes, why are most manufacturers allowing oil consumption of basically 1 liter per 3,000 to 5,000 miles before they consider an oil consumption problem?
Wow, that's a good one.
And it is, because we've got another question basically is, what is considered normal oil consumption? So those two questions kind of go along with each other. Yep.
We want virtually no oil consumption. I say virtually no. None. Nil. Okay. Why do some OEs have a spec that's fairly lenient? That was your first question. And again, this is my opinion, so you don't say, well, Bill said that it's gospel. My opinion is because they don't want a bunch of them coming back on warranty issues. If they said it should use no oil over the whole life of the service change of the oil, 10,000 K or whatever, and it used oil, then they would be liable. So I think that's why they tend to be a little bit on the lenient side on what they consider normal, is they don't want a bunch of engines coming back. Now, I don't think you should read into that it's really normal. Normal oil consumption is very, very little oil consumed during the cycle of that engine. Matter of fact, I'm driving a 2015 Chevrolet 5.3 liter V8, and it doesn't use any in 10,000 miles. Well, that's what it should be. I don't add oil between oil changes on that engine, and that's really the way it should be. And my poor old Ford that died this summer with over 300,000 miles on it, it would run an entire oil change, 10,000 miles, and never use any oil. That's how it should be. So I think that what's acceptable is very, very little. And I'll tell you a real quick story here too. We got a minute. I'll tell you this story. At Muskegon, where we do our research and development on piston rings, Muskegon, Michigan, that is, we actually do a EPA oil consumption process. And what we do is we take the engines and we add a radioactive isotope to the oil. And we run those engines through an EPA cycle in our dyno cells. And if they're using any oil, it goes, of course, through the exhaust, and it carries that little isotope tracer with it. Well, then we use a distillation process, and we distill the water vapor out of that exhaust, which carries the isotope with it. And then we use a means of checking radioactivity to actually determine what is the oil consumption in that engine. And we do that because it's so small, we couldn't measure it. We couldn't use a measuring cup or whatever to measure it. It's very, very small. But we're able, by measuring the radioactive isotope, to do that. Matter of fact, it's so accurate that our OE customer, I won't mention their name, but our OE customer uses our data for their data when they turn it into the EPA. So they have complete confidence in our lab and what we can do. So that's how little oil that engines are consuming when they're run properly.
All right. What we're going to do is we're going to go to one more question, and we're going to do a little bit of housekeeping just for those of you that need to get on with your day. But we'll still, Bill, if you've got a little bit of time, we've got quite a few questions, so we can hang on for a little bit if that works out for you.
Works for me.
Okay, so let's ask one more. We'll go one more question, and like I say, we'll get Amanda back on to do a bit more housekeeping here. So is ring tension more affected by crankcase windage or cylinder pressure? Seems everyone is kind of pushing the low tension rings now. Some concern about low tension. You know, what is your feeling there?
Well, read that again. Let me. That was a,
sure. So is ring tension more affected by crankcase windage or cylinder pressure? It seems everyone is pushing low tension rings now. Some sledge engines concern me about low tension.
Okay, so it's a yes and no, kind of a yes and no thing. Ring tension is affected and created by the gas pressure behind the ring forcing it out against the cylinder wall. So whether it had 7 pounds of unit pressure, non-running, or whether it had 20 pounds of pressure, if we're loading the ring with gas pressure when it's running, it's immaterial what it's got. Okay, as long as it's got enough tension to get the thing started, we don't care. But whoever sent this question in is very savvy. If we get pressure below the ring pack, crankcase pressure, in other words, or windage pressure, as they refer to it, that can affect how much we can load the ring, because now we're having trouble evacuating that little bit of gas. Remember, we talked about how it gets caught between the rings. Well, if we got a lot of crankcase pressure we're not dealing with, it's going to be difficult to get the gas past there. It's going to be difficult to load the ring. But otherwise, low tension is good, really good. Matter of fact, it reduces friction in the engine and gives us more power. So there's nothing wrong theoretically with low tension. But whoever sent that in brought up a good point. You know, we have to have all our ducks in a row. And if we're not evacuating pressure out of the crankcase properly, then we're going to have an issue sealing any ring, and probably an issue even more so sealing the low tension ring. Okay?
Super. So I'm going to go back to Amanda here just for half a sec for us to do a little bit of housekeeping for those of you that do need to get on with your day. I do have lots of questions here, so you know, I'll go back to Amanda, and then we'll get back to you, Bill, with some questions.
Okay.
With some more questions.
All right. So just so everyone knows, those of you that do have to get on with your day, when you leave, there will be a survey that pops up. And in that survey, if you have any follow-up questions for Bill, there will be a spot in there to enter those, and we can get back to you later. You'll also get an email tomorrow with a link to a recording of today's webinar that you can use at your convenience, pass on to people within your shop. It's yours to do with as you please. And lastly, you'll see our contact information for myself, Rob, Steve, and Karen at AERA. You're welcome to call us anytime with questions, and we can pass them along to Bill if needed, or make sure that you get taken care of. So for those of you that have to go, thank you for joining us. And we will switch things back over here and get some more questions answered.
All right, thanks, Amanda. So yeah, back to you, Bill. Another question is coming in. Do you have any generalizations about finish versus ring material?
No, we talked about that, and I'll real quickly go back over that one more time. No, and the reason is ring manufacturers, and I can guarantee we do at MAHLE because I've stood there and watched them. We take a ring and we lap the ring up and down in a cylinder with fine lapping compound. And we do that to all our compression rings, no matter what the material is. So the surface finish of the ring, it's pretty much what we call pre-broken in when you get it. So it's been lapped in a cylinder. So whether it is PVD or whether it's a regular Gen 2 MAHLE or whatever, the surface is going to be pretty much uniform. Now, by the way, the reason we lap them in that cylinder is that's how we create the barrel face, the little radius that's on a ring face. And again, we could spend another half an hour talking about rings, but most compression rings today are barrel-faced compression rings, and that barrel or radius is put on there in a kind of trippy, high-tech lapping process. So, nope, doesn't make any difference.
All right, Kate. Here's another one that shops have to deal with all the time too. Is there any negative effect to ring break-in using modern synthetic oils?
Man, we need Lake speed here. Where's Lake at? So anyhow, I do not think so, but I don't know. If you feel more comfortable breaking in, using a break-in oil, and I know Lake sells a break-in oil. So if you feel more comfortable using a break-in oil, I'd say go for it. Now, I will tell you this. I am 100% an advocate of high-tech oils, okay? Synthetics, in other words. I run them in my vehicles. I have for years. I wouldn't run anything else. So I'm a huge advocate of synthetic oil. But you may, look at the break-in oil. So I waffled on that a little bit, Rob, but I don't know.
Yeah, no, and we've actually got Lake is doing a presentation for us coming up in May. So we do get that question on the tech line a fair bit. So it'd be a good one for him for a webinar for when he's doing in May. We'll ask him that for sure.
Yep, be a good one.
Yep. Another one, and you might not quite know this off the top of your head, but they've asked, what is the proper range of back clearance on compression rings?
Oh, that's a good one. Yeah. It's kind of like what's the minimum end gap. What the proper back clearance is just enough that we don't have any problems. And I'm laughing because when we went at MAHLE, I speak of we now MAHLE, when we went from cast iron compression rings to steel rings in all our top 90% of our line in the aftermarket is steel top rings now. They had less radial wall thickness than the cast iron they replaced. And that's because the steel has more unit strength than cast iron. And if we'd have made the ring identical to the cast iron ring, it'd have been like a 35-pound ring. Well, we can't have that. So we reduced the radial wall in order to do that. Well, right away, we got lots of calls from savvy customers saying, wait a minute, you got all this back clearance back here. So we were concerned. So we went to our lab and we ran some tests, and we could not measure any difference in blow by, any difference in performance by increasing that back clearance, substantially. I'm talking now probably a 20 thousandths increase in back clearance. And now again, this is a stock replacement ring set. I'm not talking about racing engines here, but stock sets. If you got some back clearance, you're good to go. Now, I want to caveat here. We talked about how important pistons and rings and applications are. We can run into a problem where we don't have any back clearance because we got the wrong piston and ring combination. And if that occurs, we're going to have major damage. Even when we get the engine assembled, we're going to have a major issue because the ring is forcing itself out against the cylinder wall. We're going to scuff the ring if we don't damage it on installation. So we need back clearance. How much on a stock engine is probably really nothing to get concerned about.
All right. Here's another one that's come in. I see the color. I see grain occurring at the top of the cylinders on my two-stroke snowmobile engine running chrome rings. Is this indicative of a piston ring problem, or is this some sort of early wear preceding bore polishing?
Better read that to me again. Is it green or gray?
Yeah, it's so I see grain occurring at the top of the grain is in the color. Yep, at the top of the cylinders on my two-stroke snowmobile engine running a chrome ring. Is this indicative of a piston ring problem, or is this some sort of early wear preceding bore polishing? That's a tough one.
I don't know.
Yeah.
It could be just it could be deposits from the oil, and fuel being consumed. I don't know. I'm sorry, I just don't know on that.
what I'm going to do on that one, I'll reach out to the person that asked the question. I'd like to see some pictures. That would help us out a little bit too.
Yeah.
So
and we have, by the way, you know, I'm old and I'm retired, but I go to the office. I'll be at the office next week. We got a lot of resources. Matter of fact, we have a whole division that sells into the power sports market. So yeah, Rob, if we could get some more information on that, we could probably dig into that a little bit further.
Okay. All right. A couple more questions here for you, and then we'll wrap things up for the day. What has been your experience with controlling blow-by with the different ring materials?
Well, good question. Again, stock naturally aspirated engines, yeah, control and blow-by should be not a variable regardless of the ring material. Shouldn't be an issue. Okay. Now I go back to my days out there, and I have spent a lot of years out there in the top fuel business. When we went to PVD top rings, we saw substantially less pan pressure. That's how they measure blow-by, is pan pressure. We saw substantially less pan pressure than we did when we were running ductile rings with a MAHLE face coating. And I believe the reason was twofold. One is the PVD rings didn't wear. You know, we would wear those MAHLE rings in 1 4-second pass. It'd be substantial wear. PVD didn't wear. Okay, so I think that was one issue. The other is, and I talked about this a little bit, the unit strength of steel versus cast iron. The unit strength of steel is superior. And I could show you some slides. In an engine that's making 12,000 horsepower and 8 cylinders, 500 cubic inch, we're literally bending the ring down in the groove as it sticks out of the land. Once it's not supported by the land, that gas pressure is literally bending that ring over. And of course, when the ring bends, we're going to have more blow-by. But going from cast to steel, ductile to steel, we got significantly more strength and reduced it. So again, stock engines, it shouldn't make any difference what you got. When you get into lots of power and lots of cylinder pressure, yes, steel is the real deal.
Okay. All right. Well, there is more for those of you that still have some more questions. What we'll do is we'll get those over to Bill, and we'll get those answered. We do got to let everybody get on with their day here today. And again, lots of really good questions. Bill, we had lots of good comments about your presentation. So very, very good job. Very informative. We appreciate your time. We know your time is valuable. And again, thank you very much. And to everybody, like I say, we'll get those questions over to Bill, and we will get back to you. So
sounds
Bill,
good, Rob. Matter of fact, I'll be in the office. You know, I got nothing else to do anymore, so I'll be in here tomorrow, and I'll be in here over the weekend. So you get the questions, and we'll get them answered. Okay, sounds good. And like I say, from AERA and everybody out there, thank you very much, and have a good rest of your day. Thank you. Thanks, everybody. Bye now.